files. Oh my God. This stuff is just, it's the perfect way to end 243 because it takes us right back to the beginning, all the way through to the end. Almost everything is wrapped up in this thing I like to call the mighty central limit theorem. The mighty central limit theorem. Don't worry, we're not proving anything. If you want to, it's called a theorem, which means mathematically you're supposed to prove it. If you want to prove it, I put it online for you on the Enrichment page. Chances are I'm guessing you don't. That's totally fine. I'm not going to tell you something that's not true. But here's all those pieces put together into one place. And Lauren, your points are well addressed right here. So, this is the whole point of statistics. You want to study a population, but you don't have the funding and or the lifespan of Yoda to go and count your population, right? They're too big. They're too big to go count. But you want to know what the average and probably the standard deviation are because that's kind of what you're interested in. Does my reading program actually do anything for these third graders? Does my new hot water hydrotherapy help geriatric patients with rehabilitation of their muscles? Which sounds ridiculous, except that was a study my cousin did about 1.5 years ago that I helped her with. This is the kind of stuff that you guys are going to be doing at some point, or at least reading about at some point. So the studies you're either going to do yourself or you'll read about them somewhere. This way you can understand them. But you can't get that, nor can you get that. The best you can do is do a random sample. And I'm going to call it size n, just because I throw that number out as a variable. Because just like we were variabling, made up a new verb there. We were using the 4 and the 9. You see now why I use numbers like 4 and 9 and 16 and 25? Anybody else wondering why the hell I was picking those weird numbers yesterday? Good for you, because they square root nicely. Yes, that was the point. But in general, you don't care about that because technology takes care of the numbers for you. You could very easily sample 60 people, and the square root of 60 is just shy of 8, so you would divide by just shy of 8. I mean, the technology can handle that no problem. But when you're first seeing it, I wanted to make sure that it makes sense to you guys. So, the first thing, and you guys already figured this out, the first part of the central limit theorem, and I made up a symbol for this, hope you don't hate me for it. That sample average that you get, whatever that sample average is that you got from your study, lives on a bell curve. Susan, one of our many bell curves. It's a point on that curve somewhere. You don't get the whole curve. Sorry, Lauren. I know I want to have it. You don't get the whole curve. What you get is you get a piece of that curve. So that little average you got is like the piece of this huge puzzle that you can't see, which maybe seems a little bit cruel. You did all this work to collect all this data, you get this beautiful, beautiful little number. But there's two things that make you feel better about it. And the first is that it's bell-shaped. Now, why do we care? Why are we so happy when things are bell-shaped? Because once something is bell-shaped, there are percentages we've been using all term long that we got for free. Yeah, essentially for free, mathematically free.
Standard deviations are easy to detect.
Yes. 2 standard deviations is like industry standard for the most part. 95% of the data is within 2 standard deviations. That's a beautiful thing to kind of keep in the back of our head. When you look at that original distribution, even if you could see it, you can't do anything with it. It's highly skewed. But the bell curve, 95%, 2 standard deviations, it's gorgeous. It's gorgeous. So, and the best part is the middle of it is right on mu. So that's like 2 yays in a row. We get a bell curve, which means we can use all the cool tools for bell curves. Yay. And then the bell sits on where mu should be. Hot damn. Now I made up a symbol down here at the bottom. Hope you don't hate me. X bar would be your sample average. X double bar would be the average of all of those averages. So this is a bit of a fictitious statement because you don't actually get that, you get that, right? But the average of all the averages is equal to mu. Just another backstory for you. I was the worst student ever in Math 360, or Stat 371 back at the University of Delaware. I had 2 or 3 stat courses as an undergrad math major. And I remember learning this in Stat 371 or 2, whatever that was, 202. And I always got nervous in a stat class when I see an equal sign. I'm used to squiggly equal signs. What's 2 plus 2? Nah, 4. That's right, ish. Ish. You learn how to ish in statistics classes, right? You learn how to ish. You learn plus or minuses. When I see equal signs, I'm like, do you mean like equals equals? Or I mean like equals equals? And the prof is like, what language are you speaking, dude? And I'm like, is that actually equality? Is that exactly equals? And he's like, yes. I'm like, holy crap. How can that be true? Because the ones we just looked at weren't exactly equal. They were bouncing around. But that's because you didn't have every single possible combination. You had Most of them, but not all of them. And he's like, well, mathematically it averages out. I'm like, yeah, but how? And I'm that guy. How? Why? How? Why? Notice all those questions in your exam. What do you think? How do you think? What do you take away from this? That's a direct result of how I am. And he never told me. He left me to discover for myself, which is now proved on the page if you're interested. There's a reason why that's equals and not squiggly equals. If you want to see it, I know you don't, but if you want to see it, it's on that page on your website. But I don't want you to focus too much on that. That is true, but here's the problem. And guys, you're going to have this PowerPoint. It's already available as of Tuesday. It's still going to be up today. You don't have to write this stuff down if you don't want to. It's all going to be given to you. It's already given to you. Here's the problem, though. Lauren's going to tell me that, yeah, that last statement's great, but this is more realistic for me because my average isn't equal to mu. Remember the curves? They're wide. I mean, yeah, it's most likely that it lands in that bar around mu, but there's still a chance it's off of it somehow. So this is, hopefully you see why this is true. It's not going to be exactly equal. It's going to be close to. But of course that begs the question then, what is close, right? What is close? So what is close?
Accuracy.
Not accuracy. Precision. We are guaranteed accuracy by step one. Richie, I know, and I love these terms because they actually carry with other classes. We are guaranteed accuracy by the second yay right there. The fact that bell curves land where mu is, that's accuracy. That means even though I can't see the bullseye, I'm hitting it in the middle on average. The problem is, how well am I hitting it? Am I hitting it like this? Am I hitting it like this? Am I hitting it like this? I mean, that's the next question is, okay, I can accept that statement right there as long as I can get close, but how close is close? So we developed a measure for that you guys just discovered. This is the measure of precision. It's got a very specific name. You might see it in research journals from time to time. You may have already seen it. It's called the standard error. Standard error. It's like a standard deviation, but it's inferential instead of descriptive. This is why I like this. This is kind of like a stepping over to 244. The standard deviation of your sample only lives in your sample. It's how far, on average, your sample data deviates from its sample average. If you try to use that and apply it to a population, you'd have to make the adjustment that we just did, because when you replicate those studies over and over again, the bell curves show up. Well, time out, that means we have to adjust our variation. The averages stay in put, but the variation is actually changing. And you guys just discovered this is how it's changing. That standard error, or standard deviation of your distribution, is the same thing as sigma, and this is the part you guys just figured out, divided by root n. Freaking rad. Totally freaking rad. You see that in everything we do in Math 244, you're going to see a root n in the denominator, and that's just so damn cool. It just keeps going. Remember me? I'm the central limit theorem. And there it is again. Every day, the students are now putting, where is it going to be, rule? The denominator. Which one? Every day. Every day. It always shows up. Because the more you sample, the more precise you get. So what do you think you do with this once you have it? What do you think you do with this? See, now you've got an average. You've got your sample average, right? You've got your x bar. And then you've got this off of your sample as well. Now, some of you are going to say, wait a minute, time out, hang on, damn it. You don't know what sigma is. So how can you form this? Is anybody thinking the same thing? You don't have sigma, how can you have this number? Remember, you don't do this side. This shows up in your study. You get this in your study, which means you're getting a look at sigma indirectly. Just like you don't get mu, you get x bar, but that's a look at mu. So you get this from your study. So now your study has, for want of a better term, a standard deviation and an average. It's on a bell curve, so what do you do? If you've got a standard deviation and an average. What do you do with the standard deviations and averages? What have we been doing with it for the past, like, I don't know, 3 or 4 weeks-ish?
You go to normal.
Good! And then, but even take one step back from that. You're still normal, I love that. That's 2 or 3 days. What do you do with the standard deviation and the average? More macro, less micro. Where is the average on the bell curve? In the median, the middle, good. I like that.
You cut off the stuff that doesn't.
By going out how far?
The two standards.
Good! You slap that onto x bar to form these ranges of values, right? Now, try to see that that's what that says. It looks terrifying, except it's not.
It's on either side.
Yes! It's saying you take your sample average. You know this, right? And you know that from your study.
subtract 2 standard deviations on that side. And do the
Right.
and then add to the end.
Which means 95% of the time, you're going to trap what you're looking for between those two values. It's the bad joke from yesterday, the bear joke.
Yeah.
5 feet to the left, 5 feet to the right. We got him. It's that joke. It's a terrible joke. But that's how statistics works. When you read in the paper that 75% of Americans agree that blah, blah, that's crap. 75% of Americans do not agree. As few as 72 and as many as 78 agree. 75 is in the middle of that. But the trick is that whatever mu you're looking for is somewhere between this and this. Sure, it's more likely to be in the middle mathematically, but that doesn't mean, you saw how unlikely more likely is. And directly in the middle, depending on how micro you're looking, can only be 10%. It's varying to one side or the other of that. So what you've done is you've thrown a net to capture something 95% of the time, rather than reporting on one single value that's only going to capture, say, 5% of the time. So your net's open this wide. Suppose you don't want your net to be open this wide. Suppose you want it to open half as much. What are you going to go do? Go quadruple your sample size. Oh! How dare I just say quadruple? I just said you're going to make the net half as wide, didn't I? Why would you have to quadruple your sample size to do that? Square root of 4 equals 2, yes? Oh, damn it. So when you want to reduce it by a factor of 4, you've got to increase your sample by a factor of 16. See, that's the trick. That's when you start running out of money with your grants. I need more data. I need to do more destructive testing of Ferrari Testarossas from 1991 to find out if the airbags will inflate. Number one, there weren't airbags in 1991, number one. Number two, who the hell's going to give them to you to run a 1991 Testarossa into a wall? Funding runs out. So sometimes you have to deal with wide nets. Sometimes you have to. That's all you can do. But if you can get more data, your net shrinks down. This is not a fixed quantity. This is a fixed quantity based on your sample. But even if this is fixed, this can get smaller, right? Which means that this can become this, can it ever go to this?
No.
Why?
Because you're always going to have that one chance that it's going to be outside.
Oh, good! You always draw that outlier that pushes it outside. Good! I was thinking more mathematical. I love that explanation.
You're always cutting half the numbers.
It's that paradox again, right? The only way to make this equal 0, put it back up one slide, let's give it to you guys. The only way to make this equal to 0 is let this grow forever. Which means n would have to be essentially infinite. Exactly, right? Because if this becomes infinite, where's the mouse?
Well, it's still an exponential because you're squaring, obviously, with the square root.
Sure, absolutely, but you can't ever square root infinity. It's not a number.
But you can never reach the 0 either.
That's the whole point. It never gets to that. It can get as close as you want to that, depending on a given sample size. I have a 244 do a problem right now. Suppose you want to be able to detect an effect of at least 3 units. How much do you have to sample to detect that effect on average? And that's the question. You just keep plugging and chugging numbers until that effect becomes a threshold that you cross. That's all it is. But it's all based on this. Freaking rad. Totally rad. Now, one last little note about it. That's all. One last little note about it. You guys have already kind of nailed this. But see if that statement makes sense. Go ahead and read it. Go ahead and read it. How dare I show the damn words on the last day of class?
You did the fourth.
Get to the fourth! Where was J cubed? I forgot J cubed. Oh, it's there was J cubed. Yeah. Just explain that to me in English and not mathese.
So as your sample size gets bigger?
What happens, Gorman?
Well, it's like, that's why replication is like the gospel of science.
Oh! Okay, can I put the word good in there? Or proper replication of gospel science. Good. Keep going, sir. Keep going.
I mean, it's just because the more you repeat, the less error.
Inversely proportional. As one goes up, one goes down. So the more you can make, essentially replication of a study is increasing sample size. You guys actually, Lauren, you noted that earlier. You said instead of doing 1,000 samples of size 4, how about one sample of size 40,000? You're still getting 40,000 data points. The trick is, central limit theorem mathematically likes the one sample of size 40,000. because it allows it to shrink way down because of this result. Rory, go ahead.
I was just saying the more data you have, the more exact you can be, because if you had all the data, you would be 100% correct, right?
Exactly. Then it would be a census.
Yeah, that would be a census.
And we wouldn't call this class statistics, and we wouldn't have talked for 10 weeks.
Yeah.
Good point, friend. This is what I love this last day. Here's the pictures. Find me the central limit theorem. No, let's paint the picture. Suppose your population is the bullseye in each of these cases. The population is your bullseye in each of these cases. Okay, so the average you're looking for is the bullseye. And your study strategy is to shoot a gun at the bullseye. But you can't see the bullseye.
But we don't know our average.
Hold that thought. That's what I'm saying. You can't see the bullseye, but you can draw a random sample, which is the gun shooting at the bullseye. 2 of these are the central limit theorem in action, and 2 of them are not. Can you see the 2 that are the central limit theorem in action? Which 2 are, even though you can't see the bullseye, 2 of them would automatically happen due to the central limit theorem? Raise your hand when you think you know which 2 they are. I don't want you calling this out. Raise your hand or just raise a finger or just look over at me when you think you know which one are the central limit theorem. 2 of them you will never have to worry about, assuming you do your sampling properly. You got some fingers? Or looking over at me. All right, friends, let me hear it. Who's going to tell me? Which 2 show me the central limit theorem at work?
Bottom 2.
We know. Vote for the bottom 2?
That's what I'm voting for.
Vote for the bottom 2? How do you know?
Because of the accuracy and the precision.
We'll get back to the precision. We are guaranteed accuracy. So even though, Lauren, your point is well taken, you can't see the bullseye, the random sampling is going to guarantee that we targeted it on average. Now, tell me about the sample sizes of these 2.
Smaller, larger.
I vote for smaller, and I vote for larger. That makes perfect sense, doesn't it? Precision, higher precision, more tightly clustered. We got a high precision here too, don't we? We also have what appears to be a faulty scope. Because we're very tightly clustered, if we're aiming for the bullseye, we're missing the bullseye. Central limit theorem won't let that happen. It says if you do the data collection properly, big if, random sample. 12 letters, very important, random sample. You collect it properly, that's not going to happen. This is going to happen with the same sample. These have the same sample size, as do these. But that's the central limit theorem. Because there's no accuracy up here. Low accuracy, low precision, low accuracy, high precision, but low accuracy, gone. There's your central limit theorem. Well, you're guaranteed 1, and you get better with more samples. That's kind of the sliding scale of precision. And that's what's so fun about it. You can pick your sample depending on how precise you want to be. Very often when you read a Gallup poll and they say, you know, what I always defer to is Congress is less popular than syphilis. I love that one. They draw a sample of like 1,200 Americans. And you're just like, what's 1,200? Where does 1,200 come from? They know that with 1,200 respondents, they're going to be within 3 percentage points of the actual percentage. So they know they've got a set level of variance they're allowing in the sample. More than 244, I don't want to get too far ahead of that.
So they have to have more, as the population goes up, they have to have more than 1,200?
Nope, has nothing to do with the population size. Oh, one of the coolest things in 244. We'll do it in 244, I promise. And this is the only thing, I bring this up only as an afterthought. I kind of hate doing it, but it's a yay to the fifth, so why the hell not? For some reason, and if you go to OSU and do some research classes, you'll see this number over and over again. There's a hand-me-down number from statistics that says you have to have at least 30 for this really to kick in. You have to have at least 30 for this really to kick in. Now you know that's crap, because we just saw it happen with 4. So I don't know where 30 comes from, honestly. I'm still researching where this number 30 comes from, but certain people love to quote, gotta have a sample size of at least 30, gotta have a sample size of at least 30. Some of you are going, why would you ever have a sample size of less than 30? To which I respond, sometimes you have to. We're going to measure how much oil came out of Deepwater Horizon in 2010. Guess how many data points I had? 6. That's all I could get. That's all I could pull off of a YouTube video that was out at the time. Okay? So I pulled 6 data points. They were damn good ones too. Hella good ones. And they were ugly, but I did good statistics on my ugly data points and got really freaking cool numbers. Better than the Coast Guard, better than BP themselves. Weeks before they admitted to how much oil actually came out of that thing. They came out the first day, like, we're losing about 100 barrels a day. I'm like, I'm watching the YouTube video. I'm like, you're using like 100 barrels a second. 100 barrels a day, my ass. And I ran some calculations, got depressed because I'm a hippie. I made my class do it with me and got a confident, I got a net. I said it's at least this much and it's no more than this much. And what's so interesting is about a month later, actually a month after they stopped the flow, they admitted a value they think actually had escaped. And that value was in the net. It was totally freaking rad. Totally rad. And depressing at the same time. because the amount of oil they lost over that time was equal, it was a sizable chunk of barrels of oil, a lot of oil, but then when I dug further, I discovered that it was less than a quarter of what we use as a country every day. So that pipe leaking into the Gulf of Mexico for 86 days
Pretty insane.
represents less than 25% of what we use in the country in one day.
Wow.
And that, I wanted to vomit when I read that. I'm like, oh boy, it's amazing. Get back on the bike, roll! Right up the hill again. Okay. Too bad there's petroleum in your tires. Damn it! Anyway. That's what we call 243. Hope you enjoyed your stay. We'll see you in a week. Email me if you get stuck with anything. And thank you. I learned tons from talking to you guys. Thank you for talking back. Thank you for sharing your ideas. Freaking rad. Email me if you get stuck on your exam. Don't wait till Wednesday night at midnight to start it. I know some of you are thinking about it. I'm kidding. You're not.